All right, so we introduced this big theorem called the fundamental theorem of calculus, and it is a huge theorem. We only get to kind of scratch the surface of it, but it is a really, really big concept, a really important concept, and used in a lot of applications. And so we're going to look at some different applications. And the first one, and the one that's easiest for us, is when we're given derivatives. All right, so applications of the definite integral and the net change theorem. All right, so what's unique about the fundamental theorem of calculus, you go back and look, its definition is true for any function so long as it's continuous. So the function could be a derivative, it might not be a derivative. Right? As long as the function is continuous, I can find the area or the difference in the area under it, right, using my fundamental theorem of calculus and the definite integral. What we're going to look at here in this section is specific applications where we're given a derivative. All right, and we're going to be given, we know it's a rate of change function, and how does the area under the curve relate in those cases? All right, so we're going to give a rate of change a derivative, and what we'll be doing is we'll be finding what's called the net change, all right, the exact change in a quantity using the fundamental theorem of calculus and the definite integral. What it turns out, and we'll do this more when I do a graphic example, we'll do a few examples where we'll look at this graphically and then we'll get into applications, is the area above the x-axis the positive change, right? My rate of changes are positive, so my net change is positive. The area below is negative, right? My rates of change are negative, means I'm decreasing, right? Negative slopes. And so when I find that area, it's a loss, right? Now, area itself is positive, but when it's below the x-axis, we're losing that area, so we'd be subtracting it away. All right, now I'm going to do an example when I first set this up with profit, right? I can have a gain of profit, and so the area would be above, I'd be gaining money, or I can lose profit, right, which would be the area below and I'd lose money. All right, so that's going to lead us to what's called the net change formula, and it finds the exact change. All right, remember our marginal analysis found an approximate change. Well, the fundamental theorem of calculus, when we use it with the derivative, finds us the net change, the exact change in my function's quantity from point A to point B. All right, so the net change formula works if my function's continuous, my original function's continuous, and its derivative is continuous from the point A to point B. All right, over the interval I'm taking the integration of. All right, so as long as I don't have any holes, gaps, or asymptotes, this works. And so what's different about this than the fundamental theorem of calculus? The fundamental theorem of calculus works for any continuous function. The net change formula is specifically, we know we're given the derivative. All right, this is the derivative I'm integrating. And then I find, well, this would be all possible original functions, all possible f of x, right? And this would be all possible f of x functions, right? General antiderivative. Right, but it doesn't matter if I don't find the initial value, right? It doesn't matter if I don't find the constant, because my next step is to find the net difference, right? Find the net change by plugging in my upper value b, my lower value a, and so that's what we do here. So the constant would cancel out even if I knew what it was. All right, so it doesn't matter if I know what that plus c is. It would cancel out in this step anyway. All right, and so what this net change theorem means, when I know it's a derivative, and I plug in my upper and I plug in my lower values, all right, we find the exact change in whatever my original function represented. All right, the net change in f of x as x changes from a to b. And we're going to look at this graphically first, and then we'll get into applications. The two cases are what I talked about before. Area above is positive, area below is negative. All right, so I'm going to graph an example of a derivative of profit. All right, so p prime of x, which is my rate of change of profit, all right, so it would be suppose it would be $1 per item, right, per item sold. All right, that would be my rate of change, whatever it would represent. All right, so if I'm looking at this graphically, all right, so this would be the items sold. This would be the dollars per item. All right, so profit usually starts out down here. So suppose this is how my profit function behaves. Alright, so I've got my profit function, or derivative, sorry, my derivative of my profit function. This is my rate of change of profit. Alright, so first of all, these points are important where it crosses my axes. Those are my critical values. Alright, that would be, I'm going to just say C1, C2, C3. Alright, so x equals C1, x equals C2, and x equals C3. Those are my criticals. Right? That's when my derivative equals 0 at those moments, right? Those would be my possible maxes and mins. So those would be stopping points, right? Neither increasing nor decreasing at those moments. Those would when it comes to a stop. Everywhere else, it's either increasing or decreasing. I'm going to look at this from 0 to some moment over here I'm going to call B. Right? Between 0 and B is what I'm looking at. And so what this is the areas below would be losses in profit, right? This area, I'm going to call it area 1. I'm going to call this area 2. I'm going to call area 3 and area 4. All right, and so area 1 goes from 0 to my first critical value, and area 3 would be losses, right? Whatever that area would be, whatever my units are, it would be the net loss and profit. So area 1 and area 3, we have a loss of profit. Area 2 would be a positive value, and area 4 would be a positive value. So area 2 and area 4 would be where we're gaining profit when we sell. All right, we have a gain of profit. And it's exactly, the area under would be, so this is exactly how much area I would lose and gain as my profit sales move down the line. All right, and so when I integrate from 0 to B of my derivative of profit, my rate of change of profit, well, it's the positive areas minus the negative areas, so the area 2 plus area 4, that would be my gains, minus the area 1 and area 3, that would be my losses. And so whatever that value comes out to be, whatever that number comes out to be, this would be the net change in total profit, exactly from 0 to B. Alright, and again, based on my picture, it looks like I have a gain. It looks like I have more positive area, right? Because this is a really big positive area. And so it would be a big positive number, meaning if it comes out to 2,000, so there was a net gain of 2,000. It doesn't mean I got $2,000 the whole time. Some of the time I lost money, some of the time I gained money. Overall, at the end of, producing B items, there was a total net gain in profit, or a net loss if there was more negative area. Alright, so we're going to do an example of this in like a social science example, right, with actual numbers. Alright, so suppose that we're given a g prime of t, so it's a derivative. Alright, it represents the rate of change in the amount of water in a pond. Alright, so it's how ponds increase and decrease in water based on seasons and years. Sometimes there's drought, sometimes there's flooding. Alright, and so this graph models the change. Alright, how fast the water is increasing or decreasing over the years. In thousands of gallons, I gotta remember everything's in thousands of gallons per year. And we're starting January, so the study started in 2000. Right, that's times 0. All right, remember the area below is negative, a loss, and the area above is a positive. All right, so here is my derivative graphed. All right, so again, time is years after 2000. Remember, it's the G prime is the change in water level, in thousands. I just gotta remember it's in thousands of gallons per year. Alright, so the first question. What's happening to the water level in the pond over the interval 0 to 4? So 0 to 4 is this first area, right? So times 0, which would be 2000, to time 4, which would be 2004, right? So from 2000 and 2004, well, there's that big drop in it, right? Meaning those have been years of drought in this particular region. All right, so between 2000 and 2004, there wasn't a whole lot of rain and not a whole lot of water added. And so there actually, as I know, the area was 72, but it's a loss. And so there was a net loss of 72, remember it's in thousands, so I'm going to write out 1,000 gallons of water. So the pond dropped in size by 72,000 gallons over those 4 years. Right? So there's going to be a big drought. It's losing water all that time. All right, well, we're going to look at what's happening at the next set of years. All right, so 2004, right? 2 times 8, which would be 2008. All right, so the next set, so that's here. All right, well, now there's a gain, right? This is a gain, so it was rainy years. All right, they were adding to the pond level, and so over those 4 years, there was a net gain. All right, so there was a net gain or increase, however you want to word it, of 40, I can't remember anymore, 44,000 gallons. Of water in the pond. Alright, so over those 4 years, it was raining. They gained water. Alright, the next question. The water level increasing the fastest. Increasing the fastest means biggest rate of increase. When was water being put into the water? When was water being put into the pond the fastest? When was the rainiest season? Biggest rate of increase. Well, that was what our function is, all right? Our function represents the increase of our water level, and so we're looking for this maximum value, right? The minimum would be down here. It's when it would be losing water the fastest. This would be when it's gaining water. This would be its fastest rate of gain, all right? When, again, that particular year would be a lot of rain, and so it's increasing really fast. And so, what year is that? Looks to be pretty close to 6, so I'm going to say 6. So 2006. So in 2006, the pond was gaining water the fastest. At the fastest derivative, fastest rate of change. All right, the last question. Find and interpret the integration of this function between 0 and 14. And so that's the graph that we're given. All right, 0 to 14 was over the entire time. And so remember, I'm going to basically be adding and subtracting my area. So area above are going to be positive. Area below is going to be negative. So the positive areas are 14 and 12. All right, so we're going to add 14 and 12. So, 44 and 12. And then subtract the areas below, which was 72 and 31. All right, so we subtract 72 and subtract 31. All right. Add and subtract the areas accordingly, which comes out negative 47. And don't leave your answer negative 47. Right? That negative 47 has context. First of all, it's a negative. And so over the years 2000 to 2014, the pond had a net loss, right? That's what the negative means, of 47,000 gallons of water. Right, which means at the end of the 14 years, so from 2000 they measure the pond level, and by the year 2014 there was 47,000 gallons less in that year. But it didn't lose it at a steady rate, right? Some of the years there was losses, some of the years there was gains. Overall, the gains and the losses, there was more loss than there was gains. And we know exactly how much more. There was exactly 47,000 gallons more lost over those 14 years than there was a gain, right? There was, another way to put it would be there is 47,000 gallons of water less in 2014 than in 2000. Right? That's what this net change means. Now I'm going to look at a couple of examples, and a couple of examples from the book are just getting you used to the idea of what the area, again, it's interpreting the area. That's a big part of this fundamental theorem of calculus. Well, we can now find the area under the curve. All right, given rates of change function, you should understand what that area is finding. All right, and that's what we're going to be doing applications. And so problem 16 and 22 is just interpreting area. So this is just explain what the area you're given finds in context to the application. We'll say in context. Alright, so problem number 16. So they're just giving you graphs with units. So it's the units that are important that explains what the area is finding. Alright, so the first problem, problem number 16, they're giving you an area. It looks kind of like a half a parabola. Alright, it starts here and it's moving up. Alright, then they give you a unit. So the area, this is the area that they give you. And then the important part is not just the area is positive, but the units. This is hours, and this is velocity in miles per hour. Alright, velocity in miles per hour is what the derivative is, right, of a distance function. And so what this finds, well, you can actually kind of use the units to help you, right? Miles per hour over the number of hours. And so if you kind of think about that, if this were a rectangle and I was finding the area by taking the change in the hours over the change in velocity, would be miles per hour times hours. Hours would cancel out and leave you with miles, right? If I have miles per hour times the number of hours, I'm left with miles. All right, and so the units are kind of giving away what it is. Now, in terms of the application, well, this means the area, right? We want to know what this area is. Well, that area finds the exact total miles they traveled in T hours. Alright, so an example would be, well, suppose I know the area is 90 and the time is 2. Alright, and so that 90 would mean they traveled 90 miles in 2 hours. Alright, that's the total distance they're traveling. And then these would be all of your rates of change. This would represent your speeds as you were so your speeds actually in this case would be fairly low. If I add up all of my speeds, that would give me all of the miles that I traveled. That's what this area is finding. Alright, the second one, number 22. Alright, so again, the graph actually is fairly simple, number 22. It's a parabola kind of shape opening up. Starts at 0, and then there's some time, and then this is the area that we're looking at. Alright, this is also hours, so it is very similar, and then the function is in number of orders per hour. So this would represent, something like Amazon, right? So many people put orders in at Amazon, right? And so there's the rate at which people are ordering. Well, that's what this would represent. This function would represent how fast people are placing orders online. Alright, and then the total area, alright, so this would be the speed at which that's the derivative, it's the speed at which the orders are being placed over the T hours. And so that area would represent the total number of orders placed over T hours. Alright, that's what that area would represent. Alright, gives you the total numbers. So the functions how fast the orders are being placed. The area totals would be tallying, adding up all of the orders over those hours. Alright, that's what the area represents. And so we're going to stop the video here. We'll pick up applications in business economics next time. We're still going to be dealing with areas, but now we're going to be dealing with functions. We're going to give them to you, and we'll be finding the areas graphically. So you might want to bring your calculator with you, and I will go over it on the calculator here too, but it's a good idea to kind of do it together. All right, we'll stop there and pick it up on the next slide.